Okay, so we've got gravity and we've got force of gravity, two different things. Alright, and also, I think your English is really good, but when we talk about a force, we're talking about exerting a force. So we say exert a force over there. Alright, let's go on. Let's have a look at this clip. I want you to tell me which train is moving. Is it the train that we're on, or is it the other train? Which train is moving?
I think it changes.
Check with your partner, just ask your partner. Alright, what do we think then? What do you think? Sorry, I don't know anyone's name, so I'm just going to have to point. I'm not being rude, because I don't know anyone's name. The other train, yeah? Because what? Definitely at the end, wasn't it? Definitely at the end when you can see that the other train is moving and this building is here. Anyone else got a different idea or same thing?
I guess maybe the first one, because they are connecting to each other. Like when the first one moving, they were carried
The first one, you mean the other train, right?
Yeah,
The other train is moving, so same. Actually, if we have a look, this building in the background is not there at the start, is it? If you look at the building at the start. So, the answer is both trains are moving at the start. But
You went with the other one.
But the point is of this is when we're moving at constant speed, or it's very difficult to tell if you're moving or not, isn't it? And what are we moving? Are we moving or is something else moving? So when you're at constant speed, it's difficult to tell whether you're moving or not.
If you're on the train, you can tell.
If you're on the train, you can tell if you're moving, right? Because you can look out the window. What if you can't look out the window?
You can feel it, like, you know when you're on the
It's got a
metro
little
and
bit
it
of a
pulls?
bounce. Yeah. If it's not totally smooth, you can feel it. Good. Okay, so when we are traveling at constant speed, it's difficult to tell whether we're moving or not. For example, we take rest or stationary to mean at rest. But if we say at rest stationary, for example now, am I moving?
like
Excellent. Well done, isn't it? So I'm not moving. The Earth is going around the Sun. Not only is the Earth going around the Sun, but it's rotating on its axis, isn't it? So it's going like this. So technically, we're all moving, aren't we? But so when we say stationary at rest, what do we mean? Well, we mean stationary at rest relative to the Earth, isn't it? Yeah? Of course, we're all moving. Newton noticed that the rules of physics apply the same whether we're at constant speed or at rest, like we said. Hence Newton's first law of motion. This is Newton's first law of motion. An object is at rest or at constant speed unless acted on by an external resultant force. Okay, so at constant speed, you don't feel any force. So the situation is the same as when we're stationary. As the girl at the front pointed out, when you're on a train, you do know you're moving because it goes up and down, doesn't it? Yeah? But if it didn't go up and down and it didn't have any windows, then we wouldn't know. We wouldn't be able to feel if it was moving or not. To change the motion of an object, we need to apply a resultant force. And this is a key issue here, resultant force, not just a force. Okay. Isaac Newton, he went to Cambridge University. I know a lot of you thinking about going to university. If you're considering physics, Cambridge University is number 2 in the world. If you want to be a famous scientist or a famous physicist, you could consider Cambridge University. Isaac Newton went to Cambridge University. James Clerk Maxwell, Stephen Hawking, a lot of famous people. What did Newton discover? 3 laws of motion. Well, we've just talked about one. His laws of gravity, which we won't talk about today, and also calculus, which is like equations relating to the world. So if you're not into science, you can blame Isaac Newton for why you have to study science, physics mainly. Okay, force, what is it? What do we mean when we talk about a force? Well, in physics, a force is any interaction that, when unopposed, will change the motion of an object. Interaction normally means the coming together of 2 objects by interaction. So if there's an interaction and it's not opposed, then we can say there's a force. 2, force is a vector, so you need to specify the direction in which it acts. So if we say vector has, what's the difference between a vector and a scalar? Who can tell me?
It's a vector.
Not
What's a
sure?
vector?
Vector has
Question?
direction. Scalar has
Huh?
Vector has direction, but scalar is no direction.
Well done. So a vector has direction and a scalar doesn't have any direction. Good question. What is a vector? Well, a vector is a quantity like a force or speed. Well, speed is not a vector. Force or velocity or acceleration or anything like that, which has both magnitude, which means size, and direction. So for a vector, we need to consider 2 things, magnitude and direction. But for other things such as mass, speed, we don't need to consider direction, we just need to consider how much are they. Okay, so let's have a look. We can represent a vector with an arrow. Here is an arrow. We can say this is a vector of force, 10 newtons. The length is important. So if I want another arrow and I want to do it 5 newtons, is it going to be bigger or smaller? It's going to be smaller. It's going to be half the size, isn't it? Yeah, so the length is important. This one's going to be 5 newtons. Okay, so this is a vector arrow of force and it's 10 newtons. This is half the size as 5 newtons. Question. What is the magnitude of this vector arrow? You can tell me.
Explain.
Don't worry. Ignore Cameron. It's not here. What is the magnitude? So magnitude means size. What is the magnitude of this?
10.
You.
10.
10 newtons, isn't it? Magnitude just means size. So what is the magnitude? It's 10 newtons. What is the direction? To the right, isn't it? So when we're talking about force, we need to specify 10 newtons and to the right. And the size of the arrow is important, okay? And this one is half the size. What's the magnitude?
Oh, the other one.
Well done, it's 5 newtons. Direction?
That way.
Well done, that's good enough. Alright, this one, I haven't left myself a lot of room, but we can also go the other direction, isn't it? Based on this scale, what size would this one be?
3, 4.
Maybe 4, yeah. I was trying to do 5. But okay, now we can add vectors together. So if we add this one and this one, what would be the resultant vector? What would be the resultant vector? 15 newtons direction.
That way.
Halfway to the right. Okay, good. What if we added this one and this one? 6 newtons. Which way? Halfway, isn't it? Why? Because this one's bigger, isn't it? Yeah. So if we add these together, then we're adding this one, but this one has a minus sign because it's going in the other direction, so it would be 10 minus 4, so that would be 6 newtons, and it would be this way. Okay, good, so that's what we mean when we're talking about resultant force. Question, yeah?
Would it like right and left and right be like different in different perspectives?
It would, but if you're just looking at an exam paper and you've got a question and it says you can use left or right when you're answering a question on a piece of paper, yeah, that's okay. Yeah. For example, I know what you mean. If I'm standing here, then it's to my left, isn't it? Yeah, and it's to your right. Yeah. But if we're both looking at the same piece of paper, then it's to our right, so it's okay. Okay. Next. So that's what we're saying. Just we can represent it with an arrow. The longer the arrow, the bigger the force, and the direction of the arrow shows the direction of the force. That's fine. Also, when we're talking about forces, we already mentioned friction, which is rubbing, isn't it? Tension is when we have a rope and we're pulling. We're pulling, so that would be a tension force. Contact force is normally when we're touching, when we're standing. Okay, so, and also, I didn't bring it with me, but we've all seen like a magnet, haven't we? Pick something up. Does a magnet need to touch something to pick something up?
No. Yes.
No!
Does a magnet need to touch something to pick something up?
To pick it up, yeah.
To move it now. Like, you will touch it eventually, won't it?
Yeah, you can move
But won't it, like, if you put a paper clip in a magnet, won't the paper clip eventually touch the magnet? Because it's being attracted to it. I'm talking to you, move!
I know what you're saying. It does eventually, doesn't it? Because it would pick it up and then it would hit the magnet, wouldn't it? Yeah. But if you moved your arm away, then you could pick it up and then move your arm away and keep moving it away. You could pick it up without touching it, couldn't you? Yeah. If you were quick enough, you could move your arm away. You wouldn't need to touch it. So these are non-contact forces. We know gravity, don't we? Gravitational force, quite amazing. Magnetic force and electrical force. Just now we're talking about magnetic force. We know magnets can attract. We just said if you can pick something up with a magnet. What else? Can they repel? Yes or no? So magnets can both attract and repel, isn't it? What about gravity? Can that attract and repel?
probably attract.
Your own knowledge of gravity, of being on planet Earth. Can gravity repel?
What about other?
I mean, if you jump back,
Why don't
that's
all
not
the
doing it.
planets touch each other? Like, if gravity is so strong, how come like, planets aren't together?
That's
Aliens.
Good question, thinking out loud. But answer to my question is no, gravity can't repel. So it's different, isn't it? So there are other forces. So maybe we're thinking, what is gravity? Right? We know magnets, that's to do with the way that the electrons line up in iron, isn't it? Yeah? Iron is the magnetic material. But can magnets pick up anything? Yes or no? No, only iron, isn't it? Or materials that contain iron. And that's to do with electrons. But gravity, is everything affected by gravity?
Yeah.
Yeah, so that's a strange one, isn't it? We know why a magnet attracts iron, but we don't know why. Why does Earth attract everything? Yeah? What's the reason? We don't really know it. We can explain it, can't we? But we don't know why. All right, let's go on. Okay. Just talking about a woman. She went. I'm not sure the name of this actor, but it was at the Oscars. I googled it, but let's just resolve the forces acting on this woman here. So, can anyone tell me a force? Good, start. Don't forget, when we're talking about forces, we need a direction. Force down, isn't it? Yeah? Force down, we say gravity, but we should be saying force of gravity or what? Force of gravity or what? What acts down? Weight, someone said it, well done. is the same size as this arrow. Yeah? So she's not moving, resultant acceleration is 0. Alright, next. Here's my car, parked outside. Maybe it's my car. Right, force down is what? Weight, well done. Force up? Same. It's not moving, is it? So we're only considering these forces where it's touching. There's weight down and we need one up, which is contact force. And it'll be on the wheels, won't it? Yeah? How many wheels? 4. So each one will be a little bit smaller. And then if you add 4 of them together, it's going to be the same size as the weight, isn't it? Yeah? No resultant force. Okay, next. Jumping out of a plane. Same thing, isn't it? Yeah? Only this time are we moving relative to the Earth? Yes or no? Yeah, we are moving. So, forces. Down. Weight and air resistance. This one, I put air resistance a little bit smaller. So, if we add these together, there is going to be what we call the resultant force. Which direction will the resultant force be? Down, well done. So if we have a resultant force according to Newton's second law, which we'll come to in a minute, we'll have acceleration. Okay, so this guy is accelerating, he has a resultant force. What if weight was the same size as the air resistance? Would he keep moving or would he just stop?
Stop.
No.
No.
Keep moving. Because he'll keep moving, but his speed won't change. His speed won't change. So if you're going at constant speed, don't forget, you can still be moving, but your speed won't change. Don't forget, we're moving now. The Earth is moving.
How do you get him to stop moving?
If we get him to stop moving, we need to decelerate. So we need this bigger. We need this bigger. But we'll get to that in a minute. Alright. This one is me and my car now, and we're driving along. What's the force acting down?
Wait.
Well done. Yeah, this one was weight. This one? Contact force, good. This one? Friction. Good. This one? Air resistance, well done. And anything else? Maybe one more. Forwards motion, forwards force. What is providing, what is giving the forward force? Where does the forward force of a car come from? Fuel, good. Fuel in the what? Engine, well done. So the force of the engine, forwards force. Okay, resultant force on the first one. We're moving. Push of engine, 600 newtons. Air resistance to the left, 400 newtons. Resultant force is what? 200 newtons to the left. B, forwards force is 600 newtons. Backwards force is 600 newtons. Resultant force is 0. Does that mean we're stationary? No. What are we doing? Constant speed, isn't it? Yeah, well done. Okay, same thing here. Let's just answer these questions. Forces acting on some objects. Say whether the forces are balanced or unbalanced. This one, 80 newtons to the right, 60 newtons to the left. Unbalanced, isn't it? Well done. Resultant force is what? Nearly 20 newtons. The other left. The other left. Okay, 20 newtons to the left. So, moving or not moving? Acceleration or constant speed? Well done. This one balanced or unbalanced? I want to know some people's names. Can you quickly tell me your names? I'll try and remember them.
Everyone's
Right.
Huh? This is going to take precious time. I think it's going to be worth it.
Just
Don't
remember
forget
Nicholas
Nicholas
and
and
I had a better idea. I was going to get you to write your name down in the order that you're sitting. Just write your name down in the order that you're sitting. So you first, then you, and then you down here, and then if you can pass it to yes, and then down to the front, and then you put it at the back like that. So do make write like the lines as you're sitting. Okay. Thank you very much. And then I can ask questions. All right, the last one, middle one. I heard someone shout it. Someone was saying unbalanced. It's balanced, isn't it? Because this is 100, that's 100. So it's not moving. Could be moving, could be constant speed, couldn't it? But there's definitely no acceleration. All right. This one balanced or unbalanced? Unbalanced. Force up or down? Resultant force down. Acceleration, yes or no? That brings us to Newton's second law. For a body of constant mass, its acceleration is directly proportional to the resultant force applied to it. Resultant force equals ma. Has anyone heard of this equation before? Some of you might have heard it. Again, why do we specify resultant force? Has to be resultant force because, for example, now my forces are balanced. I still have force, don't I? But I'm not accelerating. Yeah? So it has to be resultant force. What's M? A? Acceleration, isn't it? Yeah? So force equals mass times acceleration, or resultant force equals mass times acceleration. This means that an object will accelerate if a resultant force is applied to it. So if you push someone, they will move, won't they? Okay, 1 Newton is the amount of force required to give a 1 kilogram mass an acceleration of 1 meter per second per second. What's 1 meter per second per second? What does that mean? 1 meter per second per second. What's 1 meter per second? Speed, well done. 1 meter per second is speed. So what's 1 meter per second per second? How much speed per second, isn't it? Yeah? How much speed per second, or change in speed per second. And then we can normally write that. Anyone know the unit of acceleration? 1 Newton equals 1 kilogram times by meter per second squared, isn't it? Yeah, so it's the amount of mass, how much force to give a 1 kilogram mass an acceleration of 1 meter per second. And how do we say that? Squared, isn't it? Yeah? Okay, good. Physics joke coming up. Physics joke. Where have you heard this from? May the force be with you. But what do we say in physics?
May the force be equal to X. I saw
Nearly.
this on Pinterest.
What do we say in physics?
What do you say, Nicholas?
May the what?
May the force be equal to something.
Nearly. Anyone?
Mass times something.
May the mass times acceleration be with you, isn't it? Yeah? In physics, that's what we say. Funny, isn't it? Yeah? Physics joke. No more laugh at once. Okay, right, next. Newton's third law of motion, moving on. So we just have the second law, which we need to talk about more. But I want to get through this quickly, so we'll talk about that later if we've got time. Newton's third law of motion. So we have 3 laws, isn't it? The first law, the second law, and now this one. If object A exerts a force on object B, then object B exerts a force on object A. This one's the easiest to understand, isn't it? Which is equal in magnitude but opposite in direction. If we push a wall with a force exerted by man on wall. What does the wall do? Nothing. It seems like nothing, but it actually pushes back on the man. Force exerted by wall on man. And we hear equal in magnitude but opposite in direction. So the force by the wall is just opposite, but as we can see by the arrows, it's the same size, isn't it? Yeah? This is Newton's third law. If I push you, it pushes me back. Okay? Let's have a look at an experiment where we're going to look at an interaction, highly trained physicists, an interaction between a hand and a face. And then we can see what happens.
Can we try later?
Don't try it. Highly trained professionals, not to be tried at home. Very official. Okay. An interaction between hand and face. Okay. And we're timing it. I think she's timed it accurately. Let's see that in slow motion. The force of the hand exerted on the side of the face.
Whoa.
What does the face do? Exerts equal and opposite force on the hand.
Killings.
What's your
And the last look.
What is
His nose takes a lot of force there. Brave scientist. Okay, so let's have a look. Newton's third law of motion. If object A exerts a force on object B, then object B exerts a force on object A, which is equal in magnitude but opposite in direction. So, force exerted by hand on face. What's this arrow? Same size or smaller? Same size, isn't it? Yeah? Okay, so it's equal and opposite, only the direction is different. So that's fair, right? It's fair? He slapped him and then his face hit his hand, so that's fair, right? Okay.
Who'd you rather be?
Who's brave?
Good. What we might take note of here is you might notice his face moves. His face moved a bit, doesn't it? But does that mean that it doesn't exert the same force? No, it does exert the same force because this is the force exerted on the face. So after the face starts moving, it has that force, doesn't it? Yeah? Before, when the hand is moving, it could have been moving at constant speed, couldn't it? Yeah? So what would the resultant force of the hand be? It would be zero, wouldn't it? Yeah? If it's moving at constant speed. So the face just applies this force, the hand applies this force to the face only, and we consider them as two separate objects, isn't it? Yeah? So after the face has moved, it has also exerted that force on the hand. So what will the hand do? What will the hand do? It will move back a little bit, won't it? Yeah? It will move back a little bit, according to this law. Okay. Moving on. So if the size of the force is 10 Newton, what will be the size of the force over here? 10 Newtons, well done. Okay, let's try a question. A camper van has a mass of 2,500 kilogram. A headwind, let's read. The camper van has a mass of 2,500 kilogram. It is driven along a straight level road at a constant speed of 90 kilometers per hour. Straight away, what do we notice is important? What about the speed? Constant, isn't it? So resultant force is what? Zero resultant force going at constant speed. A headwind begins blowing. So now we have a force in which direction? Headwind. Well done. Size? 200 newtons. Okay, so calculate the van's deceleration. So we can use F equals ma. We just need to rearrange it. A equals what? A equals what? F over m. F is how much? 200 newtons, because initially there was 0 resultant force. Now a headwind is blowing. Now we've got 200 newtons to the right. But is direction important? Yes or no?
Yes.
Yeah, and if we take forwards as positive, then the headwind should be minus 200 newtons divided by mass, how much? 2,500. Who's got a calculator?
You can use your phone if you want.
Oh, use your phone. Especially.
Oh, I
Bring it in,
use the
please.
real calculator.
It's for today. You haven't got one.
Fancy. 0.08.
Good. And this is kilograms. And we've got a minus there, so we can put 0.08 or 0.8?
0.8. But is it
0.08.
kilograms or newtons?
Okay, so that's the question. We can see here that the unit should be newtons per kilogram, but normally when we're talking about acceleration, we use meters per second squared, isn't it? Yeah. But we could also say newtons per kilogram. That would be correct. But normally we say meters per second squared. What if we calculated acceleration, isn't it? Acceleration in the opposite direction. So therefore, deceleration equals, deceleration would be positive, so that's going to be 0.08 meters per second squared. Okay, next question. The van begins travelling at a steady speed before colliding with a stationary traffic cone with a mass of 10 kilograms. The traffic cone accelerates in the direction of the van's motion with an acceleration of 29 meters per second squared. I. Calculate the force applied to the traffic cone by the van. One A. This is B, part 1. Alright, not too difficult, is it? B, part 1. What equation do we need? Well, it's the same thing again. So we just need F equals ma. In this case, N is how much? Where's the name list? Is the name list finished yet? I can pick on some random people. Okay, let's start with Alvin. Mass is how much? Well done, 10 kilograms. Times by 8.
29.
Per second squared.
Good, because we're talking about the force applied to the traffic cone, so we need the mass of the traffic cone and the acceleration of the traffic cone. What is the direction of the acceleration of the traffic cone? To the left or to the right? To the left, in the same direction as the van, isn't it? Yeah? Okay, 29 meters per second squared. Alvin, answer?
290.
Yeah. 290 unit.
Newton.
F.
Newton.
Newton, isn't it? Yeah, okay. Well done, Newtons. Alright, part 2. State the force applied by the cone to the van during the collision. State the force. Okay, pick on someone. Who knows the answer? I think, is it Megan? Who's Megan?
That's right, Megan.
Don't have to do any calculation for this. It's just a 1-point question.
Think about the face slapping example.
Yeah. So the force applied by the van to the cone is 290 newtons. So what is the force by the cone to the van? 290 newtons in that other direction, isn't it? Yeah? So we could write 290 newtons, and then we'll specify the direction, we'll say to the right. You could put a negative sign there, that would be okay as well, but we'll just put to the right there. Okay. Part 3, calculate the deceleration of the van during the collision. Assume all of the force applied by the cone to the van causes the deceleration. Part 3, well, let's see. Nicholas? Who's Nicholas? Ah, okay. So what equation do we need? We need that. This one, right? F is how much? Good. If we're talking about acceleration, we're going to put negative 290. That's fine. Yeah. And this is newtons, and this is kilograms. Answer is?
0.116.
Well done. Unit? Unit?
Meter per second.
Meters per second squared, isn't it? 10 meters per second squared. We've still got the negative sign there. That's the acceleration. So then we just say deceleration. You can spell it. I think that's how you spell it. Deceleration equals, and then we'll say positive 116 meters per second squared. Okay. Good. Moving on. We've got a few more minutes.
Why is there a negative?
There's a negative because it's in the opposite direction to the motion. So we're taking, all the negative sign means is direction. Yeah, it just means direction. So it means to the right in this case, doesn't it? Yeah? And the acceleration is to the left. The deceleration is to the right. Acceleration is to the left, deceleration to the right. So if we're talking acceleration and it's negative, that means it's acceleration to the right, doesn't it? Yeah? Which is positive deceleration. Right. Let's try dropping something and explaining it. I've got two balls, look the same. One is a ping pong ball, one is a golf ball. I don't want to damage the floor, but...
Go for it if you want.
which one's going to hit the ground first? Golf ball. Ask your partner and tell me. Hayley? Which one's going to hit the ground first? Golf or ping pong? Golf? Danny? Golf? Same or golf? Same time? Pretty, let's go. Golf.
Then, that's like you're going to drop them the same way.
Try to.
Golf.
Next. Golf. Next. Same. Next. Same. Golf. Right. Good question. Is it in a vacuum?
It's the same.
If I hold my breath, is that a vacuum? No, still not a vacuum. No, it's not a vacuum, so... Very scientific, isn't it?
Camera to like take
Yeah, that's what we need to do, isn't it? We need to do a camera.
Go, Danny.
Okay.
For you.
Wait, can someone take his hand and the ball? Because like maybe
You take this hand, I'll take the ball.
Sorry. You want to do it? You want to film it? Alright, sure. Let's try it. But it might not be very accurate because my hands might not be exactly at the same level. That could be one problem with it. Also, what else could be a problem? I might not drop them at the same time. Alright, let's try. 3, 2, 1, go. Alright, play it back in slow motion. Luckily, I've got one already prepared when we videoed it. This is Brian Cox, a famous scientist in the UK right now. He's a teacher at Manchester University. Manchester University is very strong for physics in the UK. If you were thinking of going to study in the UK and you want to do physics, you would have Brian Cox as a teacher, which would be very amazing.
I'm going to Australia.
You have seen this. Okay, good. You've seen this, that's good. So you know what's going to happen. Here we've got a bowling ball and some feathers. Which is heavier? Bowling ball is much heavier. Which one will hit the ground first? Bowling ball. Anyone think feather? Anyone think same time?
So what's the feather? It's open. So won't
We
it?
might have seen them. Okay, so let's see what happens. Oh, feathers going really slowly. We got just enough time to explain why is feathers much slower than the bowling ball.
Where is he?
He's in NASA in America.
They let him in. For that? For that?
So you can see the experiment.
It's just a bowling ball and feathers.
I know what you guys want to see before we finish, and then I'll try and explain this if we've got time, right? But I know you guys are going to want to see this. Yes, there's air in there, isn't it? So the air resistance affects the fall of the feather. The force down is the weight, isn't it? Which one has a longer arrow? Which one has more force down? The ball has a much bigger arrow down, doesn't it? Yeah? Air resistance increases with speed. How do you know that? Well, because if you put your hand outside the car window when you're going slowly, then it's quite easy to do, isn't it? There's not much wind. If you're doing it when you're going down the highway, it's really hard, isn't it, to hold your hand there? There's a lot more air resistance. So we know air resistance increases with speed. All we need to do is to match the bottom arrow, don't we? So the air resistance starts growing when they drop, but it gets to the feathers arrow very quickly. It matches that arrow, and then it falls at constant speed. So almost straight away, the air resistance matches the weight of the feather. The bowling ball has a much longer arrow down, so it takes much longer for the air resistance to match the bowling ball. So that's why the bowling ball moves much faster. If we did it in a vacuum, let's have a look. We take all the air out. Now what's going to happen?
He gets to go there for free.
Well, I don't know, I think the BBC might have paid it, but why is there no sound?
There is.
Okay, the sound. So what they've done is they've pumped all the air out of the chamber, and now it's a vacuum. So there's no air resistance. What happens? We can't hear the sound, which is a shame. With no air resistance in the chamber, they obviously fall at the same speed. Why do they fall at the same speed now? Well, the acceleration is the same. What is the acceleration? Well, it's gravity, isn't it? Yeah? So acceleration is the same, which means the speed, the change in speed is the same for both objects. There's no air resistance to balance the weight. So they both fall at the same. Yes, there's a bigger force on the ball, but the ball has more mass. It's harder to push something with more mass, so that's why there's more force. But the acceleration is the same, ultimately. Okay. Consolidation, very quickly. So just to recap, to change the motion of an object, we need to apply a resultant force. That is Newton's first law. If a resultant force acts on an object, then the object will accelerate. Newton's second law. When you push something, it pushes you back just as hard in the opposite direction. That is Newton's third law. Alright, let's leave it then. Alright, thanks a lot, guys. See you again in the future. If not, good luck.
Now you get to stay here for more science.
Oh, double science.